Hi everyone, we're going to begin our unit on air pollution by looking at the stratosphere. If you remember from Unit 4, Earth's atmosphere is broken into several layers. The troposphere is the layer closest to Earth's surface, and the stratosphere is the layer that's directly above that. Above the stratosphere, we have the mesosphere, thermosphere, and exosphere. But we're going to be focusing on ozone in the stratosphere for this lecture. So our stratosphere is really important because it has something in it called the ozone layer. And if we remember again, ozone is a molecule that's made up of 3 oxygen atoms. This ozone layer is between 9 and 18 miles above Earth's surface, and it's really important because it acts as a shield to keep a lot of UV radiation that comes from the sun from actually getting to Earth's surface. So specifically, we have several different kinds of UV radiation that are released from the sun or come from the sun. Those are UVA, B, and C. And if we can see in this diagram over here, UVA is the one that kind of can directly go through the ozone layer, UVB is highly filtered, and UVC is completely blocked from getting to Earth's surface. And that's because we have this protective ozone layer here that is basically like a buffer or a shield keeping away some of that radiation. So UV radiation is dangerous because it can cause sunburns in humans, it can cause eye damage, and it can also cause cancers, skin cancers to develop. So before we get into our ozone layer being depleted or broken down, we need to talk about how ozone just naturally would exist under normal conditions in the stratosphere. In general, oxygen makes up around 21% of the stratosphere, and that oxygen exists in the stratosphere as either free oxygen, so that's just a single oxygen atom, or as molecular oxygen, which is this right here, O2. So 2 bonded atoms of oxygen. So in order to make ozone, which is a molecule that's made up of 3 oxygen atoms, we need some input of solar radiation. So the first thing that happens is UV radiation will strike a molecule of oxygen gas in the stratosphere. That's what we're seeing right here. So we have UV radiation striking that molecule. That causes it to break the bond that holds those 2 atoms together, and we get a product of 2 free oxygen atoms. So 2 just single solitary oxygen atoms. So if we were to draw this equation, and I do want you to have this in your notes because when you are answering an FRQ, it's okay if you answer by using chemical equations. It's not required, but if that's what makes sense in your brain, then that's what you should be using to respond to questions about ozone formation and breakdown. So this first reaction, we have a molecule of oxygen. We have UV radiation coming in, and it's really important that you know that it's UV radiation. You don't want to just say sunlight. You want to say specifically that it's UV radiation. And that breaks down into 2 molecules of oxygen. So you can write it like that, or you can write it as 2O. Just know that this is an O and not a 0. So then what happens is that free oxygen atom that's produced by the first reaction will combine with another oxygen molecule that is existing in the stratosphere, and it will form ozone. This reaction doesn't require any input of solar radiation, so that's what we're seeing here. These 2 get together, the oxygen atom right here and the molecular oxygen or oxygen gas, they react together to form ozone. So if we're writing that equation, it's just 1 atom of oxygen plus a molecule of oxygen gas forming ozone, which is O3. So ozone in the stratosphere is formed and it breaks down naturally. So without input of other chemicals by humans, this is just occurring all the time. How it occurs is this UV radiation from the sun, it can break apart oxygen molecules, so those O2s, to form free oxygen, and it can also break apart bonds in ozone. So that's what we're seeing here. The same UV radiation is coming down, it's hitting these molecules, it energizes them, and they have enough energy to release one of those oxygen atoms and break a bond. So this equation would be ozone, O3, plus again, this is UV radiation, not just sunlight. Make sure you note that it's UV. And this forms a molecule of oxygen gas and a free oxygen. So the big idea here is that the formation of ozone and then its subsequent breakdown is a cycle. It can occur indefinitely as long as there's UV energy that is entering the atmosphere. So as long as we have the sun and we have UV radiation coming from the sun, we are going to get ozone being formed and we are going to get ozone breaking down. So under normal conditions, our ozone levels remain constant. That means that we have just as much ozone formation naturally as we do have ozone breakdown naturally. So again, this is under normal conditions, pre-human input. So stratospheric ozone, and again, I want to make it really clear that we're in the stratosphere. So this is our second layer. We are not talking about the troposphere right now. We're talking about the second layer away from Earth's surface. So ozone in the stratosphere is very beneficial. This ozone layer is really important to sustaining life on Earth because it does this filtration of UV radiation. All types of UV radiation, so A, B, and C, can damage tissues and DNA. They can cause things like skin cancer and eye conditions like cataracts. And if we're looking at these diagrams on the right, up at the top, this is something to refer to if you're worried about spots on your skin. As you get older, that's something you'll care about more probably than you do right now. And then also cataracts happens when you kind of get this cloudy lens and it really causes your vision to be blurry. Another thing that happens is UVB. So that's the type of UV radiation that is mostly filtered. Some of it gets through. UVB exposure reduces plants' ability to photosynthesize. So photosynthesis is really important. Plants are the basis of every single food chain, or photosynthetic organisms are the basis of every single food chain. So if we have a lot of UVB exposure because we have less ozone in our stratosphere, then we're going to get less photosynthesis, which means there's less energy available for those producers, less energy available for those primary consumers, and then as you continue moving up the food chain, we know that we lose most of the energy as you move upwards in that trophic level or through those trophic levels. So if we're losing out on a lot of photosynthesis or photosynthetic ability, we're losing out on a lot of available energy. Ozone in the stratosphere is being constantly formed and broken down just under normal natural conditions. Unfortunately, human beings and our activities have caused ozone to be broken down at a much faster rate than would have occurred under these normal conditions. So the chemicals that have the biggest impact and are the biggest issue with our ozone layer and deplete our ozone layer are called chlorofluorocarbons, or CFCs. And these are just molecules that have a carbon atom in the center and then some combination of chlorine and fluorine as other atoms bonded to that carbon atom. There are a few different types of CFCs, but you just have to know that there's a fluorine atom, a chlorine atom, and a carbon atom at the least. These chlorofluorocarbons were used beginning in the 1920s, and they were used in refrigerators, in air conditioners, in aerosol sprays, in styrofoams, things like that. And they were considered safe because they're technically non-toxic to humans and animals, and they're non-flammable. So ingesting them or being around them doesn't have an issue, but the big issue that does occur is they are really, really good at destroying ozone. So what happens is when these CFCs get released into the atmosphere, they travel through the troposphere up to the stratosphere. So we're releasing them in here by using them in our refrigerators and our AC units. When they travel to the stratosphere, and the first thing that happens is this UV radiation from the sun will hit these CFC molecules, and it will cause them to break one of those bonds that a chlorine atom has with that carbon atom, and it'll release that chlorine atom into the air. Then that chlorine atom will react with ozone. So when the chlorine atom is released from that CFC, it reacts with ozone, and two molecules are formed. We have a molecule of chlorine monoxide and a molecule of oxygen gas. So if we're going to write that again as a chemical equation, we have ozone, which is O3, plus our chlorine, and this is coming from a CFC. It's been broken off from a chlorofluorocarbon, and this reaction occurs and creates chlorine monoxide, which is a chlorine atom and an oxygen gas. So then what happens is this chlorine monoxide will react with a free oxygen atom that's just in the stratosphere. As we know, just having UV radiation entering can cause molecular oxygen to break apart into two oxygen atoms. So that chlorine monoxide will react with a free oxygen atom that's already in the atmosphere. This reaction has some big implications because it will free up that chlorine atom again. So we have our chlorine monoxide. It reacts with an oxygen atom and it produces another free chlorine, or it releases back that chlorine atom and molecular oxygen or oxygen gas. We can see that we are beginning with a free chlorine atom and we're ending with a free chlorine atom. So it's kind of just acting like a catalyst in order to break up that ozone. What this means is once we recreate this, or it's released again, this chlorine atom, it can go back up here, grab another ozone molecule, and break it apart again. So a single chlorine atom can break down as many as 100,000 ozone molecules. So that means if one CFC is released into the atmosphere and it releases a chlorine atom, that atom has some really big implications on our ozone layer. This depletion of ozone allows more UV radiation to reach Earth's surface, which causes harm to organisms. So it reduces photosynthesis, it causes skin cancer and cataracts in other living organisms. Since the late 1970s, stratospheric ozone concentrations have been decreasing, and they've decreased more than 25%. So it's a pretty significant decrease. Ozone depletion is greatest at the poles, and this depletion is seasonal. So specifically, ozone declines in the Antarctic from August through November. So it doesn't decline all the time, but it does decline really quickly between August and November. And this is partly because of the tilt of Earth, so more UV radiation can reach that area of Earth's surface, and also because there are some very specific conditions that exist at the poles, and what we see are these things called ozone holes that are formed. The conditions that allow this are in the Antarctic, we have very low winter temperatures, so it's super cold. And that causes the formation of what are called polar stratospheric clouds, or PSCs. So they look like this picture on the bottom right. They also allow ozone to break down much more quickly. So there are some special reactions that occur in polar stratospheric clouds, kind of on the edge of them. This is way more than you need to know for the AP test, but it's something to be aware of. And this results in really high levels of chlorine and chlorine gas. So these clouds existing there means we have more chlorine in that area of our stratosphere. So this causes more ozone to deplete because, as we know, a single chlorine can break apart hundreds of thousands of ozone molecules. So we get a lot of depletion of ozone above our poles. This creates an ozone hole, and something that is a misconception is an ozone hole doesn't mean that there's no ozone above the poles. What it means is the concentration of ozone is much lower than other areas of the stratosphere. So these are just kind of areas that have a very low amount of ozone compared to other areas. Okay, so last thing we need to talk about is something that is more positive. In response to the decrease in stratospheric ozone, scientists have been tracking this ozone depletion for years, but in response to this, we originally had 24 nations come together in 1987, and they signed what is called the Montreal Protocol, shorthand, or the Montreal Protocol on substances that deplete the ozone layer. So this protocol was very successful. It is the most far-reaching environmental treaty to date. As of now, we have more than 180 countries that have signed this agreement and also have agreed to several amendments to the original Montreal Protocol. Basically, the goal originally was just to reduce CFC production, but after some amendments, the new goal was to actually eliminate CFC production by 1996. And this has been successful. So all of these nations that are a part of this Montreal Protocol have stopped creating CFCs. They use other chemicals in their place. So they're no longer being put into the atmosphere in large quantities. The tough thing with this is CFCs are incredibly long lasting because, as we know, that chlorine atom can do a lot of damage, and it remains in the atmosphere for quite a few years. So we have stopped CFCs, which will reduce the ozone depletion that we're seeing, but there is a lag. So even though we've had this great success at removing this substance, we're seeing some lag before we see big decreases in ozone depletion. And this Montreal Protocol didn't just address CFCs, it also addressed 96 or I guess 95 other ozone depleting compounds. So this is a very, very successful protocol. As I said, we took out CFCs and we had to use some other or develop some other chemical to use in our refrigerants, in our air conditioners, and other things. And one of those that was most successful was our hydrofluorocarbons, or HFCs. So these were developed to replace CFCs as refrigerants. What's great is that they do not react with ozone. They don't cause ozone depletion. What's not so great is their greenhouse gases. So while we are making positive movements in one direction, we also need to consider all of the effects that could occur when we're adding a new chemical into the atmosphere. And so your practice FRQ for this combo of two sections is to describe how stratospheric ozone protects organisms on Earth from UV radiation. Then describe how CFCs deplete stratospheric ozone. I highly suggest that you practice writing out those chemical equations or even drawing out the actual molecules themselves so it really kind of soaks into your brain. And then I want you to explain how the Montreal Protocol decreased ozone depletion.